Let me first welcome you all to this webinar. And the first thing I want to do is thank all the people who have contributed to this special issue. It's very nice to have this as a hard copy in your hand. And it was a lot of work done by all the authors, all the reviewers, the editors, and IEEE staff to get this done. So thank you to everybody who contributed. So there might be quite a few people on this webinar who are not so familiar with fiber optics, but more with general communications. So we have a couple slides that show the intricacies of fiber optics and what fiber optics is all about. So first of all, we need to note that the optical fiber infrastructure is really the workhorse of the internet. Without optical fiber, there wouldn't be an internet as we know it today. There are over 6 billion kilometers of fiber installed globally, which is a very thin strand of glass that you can wrap around the Earth about 150,000 times, or you can go 20,000 times to the sun and back with that string of glass. And fiber is deployed on land and under the ocean, so fiber is everywhere. Now, in terms of the traffic growth in those networks, we observe a very, very nice and constant average of 45% per year. If you average that across all networks across the entire globe, of course, that means that some parts of the globe and some application segments have a higher growth, others have a slower growth. But if you look at the total transponders that are sold, have been sold, and are deployed in the network, you see a very consistent 45% per year growth, and that goes back to the early 2000s and very likely earlier than that as well, but our sources don't reach back far enough. So today we have 1 exabit per second of optical transponders deployed in metro and long-haul networks. And if you count all the optical ports that include ports also in the data center, you have 20 exabits per second of transponder capacity deployed in networks globally today, which is an enormous amount of traffic, of course. And that also shows how optics is responsible for all the traffic that's being carried around. Now, if you look at the growth of per wavelength interfaces and WDM capacities, for those of you who are not so familiar with optics, we modulate communication signals onto a laser carrier, and then we use many laser carriers in what is called a wavelength division multiplexed or WDM system. And we even use 2 polarizations of light, X and Y polarization these days, to carry information down an optical fiber. So what you see here is, as a function of the years, on a logarithmic scale, you see very nice straight lines, which mean exponential growth of per wavelength interface rates going all the way from sub-gigabit per second in the 80s, all the way to over a terabit per second today. That's what commercial systems can carry on 1 wavelength today, with a growth rate of 20% per year. Then in the mid-90s, WDM came around, and with WDM, network traffic per fiber increased at 100% per year, then saturated to 20% per year, and is now really approaching a very strong saturation where there is little hope of getting more information capacity over a single optical fiber. And that is also corroborated by WDM research. You see here research results, which also show that same trend, the strong growth in the 90s, then a saturation to 20% per year, and a very, very strong saturation now, even if you include multiple optical amplification bands like the SC plus L band. So even research is grinding to a halt here. And that's exactly what this special issue is covering, ways to overcome that capacity crunch. And there are many ways to do that, involving to some extent new fibers. So you can go ultra broadband, which is done using hollow core fibers, for example. You can use fiber bundles, those thousands of fibers in the same cable. And you can use multi-core fibers, where you have multiple optical light guides that are embedded in a single glass cladding. And you can even go denser than that and have coupled cores and few moded and multi-moded fibers, where you carry individual information over different spatial modes of an optical fiber. So we'll cover all of this in this webinar, and it's all covered in this special issue as well. So the first paper in this special issue was written by Werner Klaus and co-authors, and it's about the role of parallelism in the evolution of optical fiber communication systems. And what that paper does is it gives a very good overview of where systems are, where the trade-offs are, both for ultra-wideband and for spatially parallel systems. It brings more practical considerations to the table when calculating the capacity of practical communication systems, and that includes crosstalk and transponder noise floors. And with all these ingredients, looking at both the spectrally parallel and the spatially parallel systems, the paper comes to the conclusion that spectral parallelism is a nice to have, and it certainly helps short term, but it's not going to be able to resolve the capacity crunch, not even if hollow core fibers are being used. So both for conventional and for hollow core fibers, spectral parallelism is nice to have, but not the solution. The only solution is spatial parallelism, which, as I said before, comes in terms of fiber bundles, multi-core fibers, or few mode fibers. And the paper reviews very nicely the literature, what's been demonstrated, both in terms of uncoupled core fibers reaching to 10 petabit per second, as you see here, and multi-core fibers, that is with some coupling here as well, and the few mode and coupled core fibers here are reaching to about a petabit per second in capacity. The next paper of that issue by Mark Steif and co-authors talks about the information capacity bounds on the fiber optic channel and examines a long history of publications in terms of treating the nonlinear fiber channel using Shannon information theory. An important chart here is this one, which looks like a cartoon, but it's much more than that. And those of you not familiar with fiber nonlinearity will be very familiar, maybe familiar with the AWGN channel, the additive white Gaussian noise channel, where the capacity, that dashed line here, is just Shannon's formula. And not surprisingly, as you increase the launch power, the optical power or the signal power, the signal to noise ratio improves, and you get more and more capacity without bounds. Once you go into the fiber channel, if you hit a certain optical power level, fiber nonlinearities start to degrade the signal and degrade the signal to noise ratio, and therefore the capacity drops again. So there is an optimum launch power on the fiber optic channel, and it can be shown that the AWGN channel from the Shannon formula represents an upper bound to the information capacity of the fiber optic channel, and this blue curve here represents a lower bound of the capacity of the fiber optic channel. And that difference between the upper bound and the lower bound is really very small. It's 1.17 bits per second per hertz, which is essentially nothing. So upper bound and lower bound are very close together, which is exactly what we want of bounds. We want them to be tight. And this paper was the first one to really express that so clearly, that the bounds are very close, really. And then the paper summarizes very nicely what has been achieved in the lab in terms of spectral efficiencies as a function of distance. Here you see various transmission experiments and how they approach their relative Shannon bounds, which is also discussed in the paper, why they cannot come closer and what the problems are as a function of distance as well. And then you also have the fiber throughput as a function of distance here. The throughput is the spectral efficiency essentially multiplied by the WDM bandwidth. So that's the absolute capacity that the fiber can carry. This is just the spectral efficiency or the capacity per unit bandwidth. It's a very nice review of all the experimental results. Okay, so with that, I would like to hand it over to Kazuhide Nakajima, who covers the second part of the papers.
Thank you, Peter. First of all, I'd like to thank Okay, thank you, Peter. First of all, I'd like to thank to all contributors for this special issue and for this webinar. And from my side, I'd like to introduce several papers with respect to 6 technologies. These are coherent data center interconnect, flexible networks, ultra-wideband devices and systems, and high-density cable and weakly coupled multicore fiber. Okay, first I'd like to start with coherent. This paper was written by Kobayashi-san and entitled Coherent Optical Transceivers Scaling and Integration Challenges. In this paper, authors review the recent progress on the digital signal processing and discussing about their future directions. And the left-hand figure shows the 3 elements for realizing high-speed signals. These 3 elements are first one is symbol rate, and second one is higher order modulation, and the third one is multi-carrier technologies. And it should be noted these 3 technologies are closely approaching to their fundamental limit. So this paper pointed out we have to consider the increased amount of optical and electrical integration. If we consider the higher integration, we can consider 3 technologies as shown here. First one is port level integration. Second one is carrier level integration. And the final one is increased density. And this paper pointed out photonic integrated circuit, PIC technology, would be a key technology for increasing the higher density, for realizing the higher density in a cost-effective way. And next paper discuss about the data center interconnect. This paper was written by Dr. Z, entitled Scaling Optical Interconnect for Hyperscale Data Center Networks. And in this paper, left figure shows traffic growth in metal DCI capacity. And this figure reveals that the annual rate of about 100% has been achieved. So these trends reveal that DCI has been a main drivers for optical transport network technologies. But if we look at some technical growth in 3 technologies in the right figure, this figure shows switch chip speed and optical speed increases 2 times every 2 years. On the other hand, serializer and deserializer speed increases 2 times every 4 years. So these trends imply that DCI will need higher and higher parallelism in future. And third paper investigates about the network flexibility. This paper was written by Dr. Andrew Rode, entitled Flexible Technologies to Increase Optical Network Capacity. And when we're discussing about network flexibility, at present we have 2 important technologies, so-called flex grid and flex rate. And as shown here, flex grid can reduce spectral gaps, and it allows large bandwidth. And flex rate also enables bitrate variable transponders. However, as increasing the degree of freedom, it becomes difficult to control various resources effectively. And the middle and right figures shows case study on the cost per bit as a function of the fiber lease cost. And this study shows that cost per bit varies with not only with operation bandwidth, that is shown with a solid line and dotted lines, but also with the network scale, middle figure and right figures. So, this paper pointed out that it is very important to effectively manage various resources, particularly when we will introduce much more bandwidth and much more optical fibers. And next paper discussing about network flexibility viewpoint from optical switching. And this paper was written by Professor Dan Maron, entitled Optical Switching in Future Fiber Optic Networks, Utilizing Spectral and Spatial Degrees of Freedom. And in this paper, authors introduce one considerable technologies for realizing a future optical switching. And that is so-called SPOC, Spatial and Planar Optical Circuit, as shown here. And the SPOC can realize effective switching by combining the PLC front end and LCOS-based optical free space optics. And SPOC can integrate multiple wavelengths selective switches. And by using this technology, we can imagine effective switching node architectures. And the right-hand figure shows the image of the switching node. And if we consider the traditional 1 by n and n by 1 WSS, we need a very complex configurations. But we can realize much more effective switching node by employing SPOC technologies, as shown here. So in this case, n by n WSS was achieved by using the SPOC. So this paper pointed out if we will effectively use the SDM and WDM, in this case, we need further study on the new optical switching technologies and node architectures. And next, I'd like to discuss about ultra-wideband devices. And this paper was written by Dr. Naldier, entitled Devices and Fibers for Ultra-Wideband Optical Communications. In this paper, authors carefully, precisely reviewed current technologies of various optical devices, such as lasers, modulators, and detectors, and so on. And this slide shows a summary of the current status of the optical amplifier technologies. Left-hand table describes the current status of the doped amplifiers. And in the middle, this figure shows the example of the SOA-based ultra-wideband optical amplifier technologies. And the right-hand figure also shows dual-stage Raman-based wideband amplification technologies. And this paper pointed out that it may be difficult to realize ultra-wideband transmission systems by using newly developed devices, but it is important we can open up new transmission window by combining the adequate devices, taking into account the requirements of the target application area. And next paper also investigate about the applicability and reality of the ultra-wideband transmission systems. And this paper was written by Hoshida-san, entitled Ultra-Wideband Systems and Networks Beyond C plus L1. And in this paper, they also reviewed the availability of current technologies in the device level. And they pointed out that it may be difficult to realize ultra-wideband devices in near future. But in this paper, they pointed out we can consider a whole band wavelength conversion technology as alternative to realize ultra-wideband transmission system in near future. As shown here, in this case, we can easily imagine how to realize virtual X-band systems by using the C-band subsystems. In this case, we can utilize the existing C-band subsystems and wavelength conversion systems, X to C and C to X conversion. We can realize virtual X-band subsystems. And similarly, we can also realize a virtual X-band WDM transmitter and WDM receivers. So this paper concluded that we can consider the new band subsystems by using the C-band existing components and whole band wavelength conversion techniques. Okay, next I'd like to introduce high-density cable technologies. This paper was written by Sasaki-san and entitled Ultra-High Fiber Count and High-Density Cables Deployments and Systems. In this paper, they review the recent progress on the high-count fiber cable systems. And in the first section, they review the some enabling technologies. For example, as shown here, we can consider fiber geometry to realize a higher density in the cable. So as you know, we have already been utilized thinner coating diameter optical fibers, for example, 200 micron coating diameter. And we can also consider further reduction in the coating. For example, 165 micron coating would be available. In addition to that, we also consider the reduced cutting diameter fiber. For example, 80 micron fiber, cutting diameter fiber may improve the higher density. And one more important technology is a partially bonded fiber ribbon, as shown here. This technology greatly increases the density in the optical cable. And by combining these technologies, we can imagine a scale up in the fiber density. And as shown here, we can we can realize a 2.3 times fiber density by employing the slot rod structure and high density packed optical fiber technologies. And we can also improve the fiber density more than 1.5 times by utilizing the new type of optical fiber technologies. And in this example, we can realize 69, 12 and 12 fibers in one optical cables. So this paper pointed out that ultra high fiber count cable ecosystem can support further growth in DCI networks. And final paper discussing about recent progress on the weakly coupled multiple fiber. This paper was written by Matsui-san, entitled Weakly Coupled Multiple Fiber Technology Deployment and Systems. In this paper, authors mainly focused on standard cutting diameter multiple fibers. The concept of a 125 micron cutting diameter multiple fiber is shown here. And as you can see, if we fix the cutting diameter at 125 micron, it is totally same with the existing conventional SMF. In that case, we can pack around 4 cores in one fibers. And when we consider the deployment and standard of these type of optical fibers, in that case, it is very important how to ensure interconnectivity. That means how we can define the core pitch. And this paper pointed out that we can derive the target core pitch by considering the backward compatibility to existing SMFs. So this figure shows the design guideline as a relationship between core pitch and mode field diameter. If we'd like to ensure the backward compatibility to the existing conventional SMF, In that case, we can use the hatched region as a design target. So you can see that in this case, we can consider a 40 micron of core pitch would be a typical value for this type of multiple fiber. So this paper pointed out 125 micron multiple fiber will accelerate future deployment and standard of multiple fiber technologies. So these are my part, and now I'd like to hand over the mic to Christian.
Thank you, Katsuhide. Okay, so first of all, I would also like to thank all the authors that contributed to this special issue. It was really a lot of work, a lot of interaction. Before I move forward to introducing the remaining papers, I would like to introduce a couple of concepts that are necessary to clarify the discussion. So Katsuhide just discussed weakly coupled multi-core fibers. Ideally, in these fibers, the cores are uncoupled with each other, and the signals transmitted in the individual cores can be received with independent conventional single mode receivers. However, if we want to increase spatial density, we have to squeeze the cores closer to each other. And if we do so, the signals start coupling during propagation. So in this case, we cannot receive them with independent receivers. We need a unified receiver, which means that we have to treat the spatial channels as spatial superchannels, and we need the multiple input and multiple output techniques to retrieve the transmitted signals. Of course, this implies an increase in complexity in the SDM receiver, but a major increase in complexity comes from the phenomenon of modal dispersion, which relates to the fact that different spatial modes propagate with different group velocities. And as a result, the duration of the impulse response of a fiber increases with propagation distance, of course, depending on the fiber type. Now, in the best case, it grows proportionally to square root of propagation distance. And in the worst case, it increases proportionally to propagation distance itself. In all cases, the duration of the intensity impulse of the fiber impulse response sets really the complexity of the MIMO SDM receiver. Okay, so this paper by Tetsuya Hayashi and the co-authors reviews coupled core multi-core fiber technology. Note that they refer to it as randomly coupled multi-core fiber technology because these fibers operate in a very special propagation regime where the coupling between the cores is actually random in nature. The paper explains very well that in order to achieve this propagation regime, the cores, the fiber cores cannot be too far from each other, they cannot be too close to each other, they must be just at the right distance so that coupling is dominated by random perturbations to the ideal fiber structure, which of course are always present in practice. The paper reviews the main design criteria of randomly coupled multi-core fibers, and they explain why this propagation regime is desirable. And this is essentially for two reasons. One reason is that this is the propagation regime in which modal dispersion accumulates proportionally to square root of propagation distance, thereby considerably suppressing the complexity of the MIMO SDM receiver. And the second reason is that these fibers have an enhanced tolerance to nonlinear distortions, a fact that has been understood theoretically and demonstrated experimentally in experiments that are also reviewed in the paper. The paper also covers characterization techniques of randomly coupled multicore fibers, splicing technology, fan-in, fan-out technology, which is key to inject the signals in the fiber cores and to extract signals from the fiber cores, and cabling related issues. It also reviews the first deployment of cabled multi-core fibers, which happened to take place in the city of L'Aquila in Italy. And it reviews some of the field trials that have been performed for both data transmission and fiber characterization. The paper by Pierre Sillard and co-authors reviews a few mode fiber technology. Few mode fibers are substantially different from multi-core fibers. First of all, they only have a single core of larger area, and they support propagation of multiple modes. They're characterized by the existence of multiple groups of modes, so that modes belonging to the same group couple strongly during propagation, just like in randomly coupled multi-core fibers, whereas modes belonging to different groups couple only weakly, of course, depending on how far they propagate. The paper reviews two regimes of operation. The first is called the weak coupling. The idea here is that the individual modes are received independently of each other, in which case it is very important to keep intergroup crosstalk as small as possible. And the goal of this approach is to maintain the MIMO SDM complexity low. The solution of choice in this case is a step index profile, and this is because step index fiber have mode groups with only either one or two spatial modes. The second regime of operation is called full MIMO. In this case, all the modes are received at the same time. And here it is imperative to keep modal dispersion as small as possible. And in this case, the solution of choice is a graded index profile. The paper reviews the main design criteria for these fibers. It also reviews the main transmission experiments performed in the two regimes of operation, as well as field trials and real-time implementations, and also the first deployment of cabled few mode fibers, which again happened to take place in the city of L'Aquila. The paper by Nick Fontaine and co-authors reviews components that enable SDM by interfacing single mode and the multi-mode technology. For instance, by allowing to multiplex and demultiplex single mode signals in SDM fibers. Now, this figure shows three types of photonic lanterns. The first two are made with tapering techniques. They connect a multi-core fiber and a multi-mode fiber, or single mode fiber bundle and a multi-mode fiber. These photonic lanterns can be mode selective, which means that it is possible to use a single mode signal to excite a specific spatial mode at the input of the multi-mode fibers. And these are examples of photonic lanterns addressing 3, 6, and 10 spatial modes. This is a different type of photonic lantern made with a different technique, ultra-fast laser inscription, which is based on the use of short pulse lasers that allow to inscribe arbitrary three-dimensional waveguides in a bulk glass cladding. And this type of photonic lanterns can be used, for instance, to make fan-in, fan-outs for single-mode multi-core fibers, demonstrated for more than 100 cores. The paper also reviews a multiplane light conversion technology, which allows to convert an array of spatially separated beams into a single beam to be coupled with a multimode fiber. This device allows to use the signal carried by any input beam to excite any spatial mode at the input of the multimode fiber, and is based on multiple reflections on a spatial light modulator. This is a picture of the device used to demonstrate a 45 mode transmission. The paper reviews the main design criteria of these devices and provides a nice comparison between these technologies that I briefly introduced. The paper by Dan Marom and co-authors has been already introduced by Katsuhide. Once again, it is about optical switching in networks that make use of both spatial multiplexing and frequency multiplexing. The paper covers a wide range of network scenarios from undersea to data centers. And this is a very nice picture that illustrates switching options that are available in SDM networks, which of course depend on the regime of propagation of spatial modes. In particular, if spatial modes do not couple during propagation, as is the case in uncoupled core multi-core fibers, then frequency channels and the spatial channels can be switched, can be routed independently. Of course, switching the entire spectral content of a spatial mode is an option of lower complexity. If the spatial modes couple during propagation, then the spatial modes, all the spatial modes at the same frequency must be routed together, must be switched together. They must be handled as a spatial superchannel to make sure that they travel together from the transmitter to the MIMO SDM receiver, all the way from the transmitter to the receiver. Of course, also in this case, it is possible to switch the entire fiber content altogether, which is again a solution of lower complexity. In general, the authors point out that pure spatial switching is an interesting solution for future networks where most likely most of the capacity comes from the spatial dimension, and therefore frequency selective switching may not be necessary. The last paper by Ezra Ip and co-authors covers a topic that is attracting more and more interest in these days, as it was clear at the last OFC. And this is using the global fiber optic network for environmental sensing. And the idea is that deployed fibers can be used not only for data transmission, but also as distributed sensors. The first approach to distributed fiber optic sensing reviewed in the paper is the more traditional one. It is based on measuring backscattered signals from Raleigh, Brillouin, and Raman scattering for the purpose of performing vibration, temperature, and strain sensing. The idea here is that each deployed fiber has a well-defined backscatter signature, so that perturbations can be studied by looking at the time changes of this signature. So this is quite a mature approach, quite a mature technique, but recently it enjoyed a considerable boost thanks to the availability of coherent receiver technology from the telecom industry. So the paper reviews all kinds of applications of these techniques, the theory and the main implementation schemes that are used today. The second approach to vibration sensing, which is reviewed in the paper, according to the authors, was stimulated by the observation that the optical phase measured in a deployed cable during an earthquake produced time traces that were strongly correlated with the time traces produced by a seismometer measuring the same earthquake. So the idea here is that vibration sensing can be performed not only by using signals dedicated to sensing, but also just by looking at data carrying signals received by a coherent receiver. So in this context, the paper reviews two field trials, one showing that various events could be measured by looking at the phase of data carrying signals transmitted in a terrestrial link. And the second, showing that it was possible to observe an earthquake by looking at the evolution of the state of polarization of data carrying signal transmitted in a transoceanic link. And altogether, this is just an amazing result. So with this, I conclude the presentation of these papers, and I'll give the word, I'll leave the mic to Vaishali.
Thank you so much, Christian. And thank you, all three of our panelists, for excellent presentations today and giving us a bit of a snapshot and a look into, sneak peek, I would say, into what's covered in the papers, and really giving a good view of the state of the art and the research that's going on in this area. We have received a couple of questions, but I wanted to start off first by just touching upon the fact that you mentioned this in the issue, that this area is kind of interdisciplinary and there's a lot of people working in this area. So for somebody coming into this area, what kind of backgrounds do people generally have as they enter this kind of area and this kind of research? Could you maybe comment on that? And also, what is your feeling about the industry participation and how industry and academia collaborate really in this area?
I mean, when I can start off
Sure,
on that.
Peter.
So
Yes.
first of all, optical fiber communications is a very strongly industry-driven field. That's very clear, and you see that with the huge trade shows at the major conferences, OFC and ECOC, for example. So there is, of course, also a very strong academic community, but it's definitely there is tons of practical importance and practical impact in that field. And the background of the people are enormously diverse who work in this field. So from classical communications theory, classical communications, physicists, material scientists, you name them. I mean, it's a very diverse group of people.
And any skills you would say people should catch up on? Like, I mean, you hear the trends with machine learning and things like that. Any hot topic areas that people should really be looking out for?
Machine learning is a tool.
Yes, it
people
is.
should know as many tools as possible.
Yeah.
But first of all, it is necessary to,
Yeah.
you know, to learn what happens in a fiber, which comes down to, you know, propagation phenomena, propagation equations, modeling of this or that type of physical effect that take place in different regimes of operation. And for instance, with SDM, there are so many new physical effects going around that it's a very nice area for those who are interested and want to you know to study fiber optic transmission at a fundamental level and have an impact. So.
Yeah, so talking about SDM, I do have a question about MIMO processing. So what do you think of MIMO processing? Is it a showstopper for SDM? That's a question we have. Do you want to take that, Christian?
No. It's I mean, people are showing that real-time implementations work, and it's matter of moving forward with the technology. It's matter of developing you know, a more convinced desire of moving forward. On the other hand, it is also important to have systems that are more and more similar to what real systems will be. And for this, I'm a stronger believer that deploying SDM fibers is important, because once we have those fibers deployed, we can really check their behavior in a real environment and see whether whatever we do in the lab is still effective in the field.
Mm-hmm. Okay, I want to talk about fibers, single mode, few mode, multi-mode. You talked about different types of fibers, and I was curious to know what drives, what things do you consider when picking the types of fibers? Is it application specific? Is it based on what expected performance criteria are there, or how does that work?
I think when we consider the backward compatibility to existing systems, in that case, it is easier to imagine introduce some kind of single mode based multi-core fiber in the first stage of SDM systems.
Mm-hmm.
But I believe that if we need a further spatial multiplicity, in that case, we have to consider how to use spatial mode into the next generation optical fiber communication systems.
Okay, and then there was a question also more specifically about multi-core fiber-based optical systems. So beside cost, what factors do you think affect the implementation of multi-core fiber-based optical systems in reality?
Mm-hmm. It is a very important question, and I think there is at least two important points. First one is cost of optical fiber and cable itself. Basically, we need additional process to fabricate the multi-core fibers. So this is basically increase the cost of fiber itself. But I believe that we can develop adequate fabrication process by optimizing the current technologies. So I personally believe that we can realize similar cost with the existing conventional single mode fiber. And the second one is a multi-core fiber-based transmission system basically basically needs additional components. One of the most typical ones is fine fan-out devices. And in that case, if we introduce a fine fan-out devices, it makes additional loss in the system. But recent research provides that we can consider some type of fiberless configuration, and it can reduce insertion loss of the five technologies. But I think that we need further research on this area in order to realize actual deployment system, multi-core fiber-based deployment systems.
Mm-hmm. And then a follow-up question to that that also came up was about crosstalk. Won't crosstalk limit the performance in randomly or strongly coupled multi-mode fibers? Can you talk about that?
No.
So, I mean, in general, crosstalk that's exactly what MIMO processing is about. MIMO processing undoes the crosstalk. So for those not so familiar with SDM, but maybe familiar with coherent single mode transmission, you also have totally random polarization evolution along the fiber, and that's a 2x2 MIMO system. So if anything that you can do in 2 dimensions with a polarization evolving in a random state, you can also do in n dimensions in a multi-mode or few mode multi-core coupled fiber, where you just have, instead of a 2x2 matrix, you now have an n by n matrix that you need to deal with, but it's the same math behind it. That's the power of DSP.
Let me add that n by n MIMO is not even the main source of complexity. As I tried to say before, it's more about modal dispersion. So that takes more than the simple n by n MIMO. So random coupling is not really an issue. Those fibers are made for to work in a randomly coupled regime.
Okay. Another question that came in while Christian was presenting was, do you see the benefit of deploying NA-NF hollow core fiber in metro and LH applications?
So in the context of this special issue where we looked for fiber capacity scaling, the papers showed that ultra wideband which is what NANF would support, is not a way to solve the capacity crunch. So in that case, I mean, for capacity reasons, you wouldn't deploy it. For latency reasons, you would. So because the light travels mostly in air instead of in glass in a NANF, which is faster, and therefore you get a significant latency benefit. So for that reason, a NANF is certainly good to have in any latency limited situation. But it's not a mechanism to increase or to resolve the capacity crunch.
Got it. Okay. So now this question is for all presenters. Do you have any insight about increasing the capacity of optical fiber communication systems regarding the fiber materials? So comparing silica-based fibers with telluride and germanite fibers. And would these fibers be compatible with other optical devices?
I think that it is very interesting to consider the other material to realize the future optical fibers. But I think if we consider the applicability to long distance transmission, in that case, optical loss and transparency is the most important factors. So I think at this moment, it is a little bit difficult to consider other material compared with existing silicon-based optical fibers. But if we look at some function, if we can get a new function by employing the other material, in this case, I believe that such kind of optical fiber will be beneficial for realizing future optical network.
Mm-hmm. Okay, we're going to go back to SDM fibers. And there's a question about commercial deployment. Are there any SDM fibers deployed commercially that you might want to comment about?
I'm not aware of deployed commercial fibers that are either multi-core or few mode. There are, of course, older generation multi-mode fibers, but I think that more than one major player announced that they are going to deploy 2-core fibers in the very near future for submarine links, and one specific company announced that after that it will be the time for 4-core fibers, and then uncoupled core, and right after coupled core 4-core fibers. So it seems to become more and more real.
Okay. So back to machine learning. Are there any examples that you could highlight where machine learning methods have been used in research directions related to this area?
I'd like to note that Professor Dan Marlon's Dr. Rhodes' paper discussing about the applicability of machine learning, how to manage various network resources. That means we have plenty of degree of freedom, wavelengths and spatial multiplicity and something like that. So in that case, we need some kind of machine learning or something like that in order to realize effective management of network resources.
Mm-hmm. Okay. So I have a question related to photonic lanterns. How is it possible to incorporate a photonic lantern in a transceiver?
Well, I'm not sure, but photonic lanterns are easy to splice. So I guess that they're thought for a straightforward integration. Now, if you ask for a commercial transceiver, yeah, I don't know. I'm sure that those who are working on it could give a better answer that I can give.
Yeah, fair enough. Okay, so I just want to ask each of you to maybe, just have one comment, which you think would be the biggest opportunity or the biggest challenge in this area, and you can just focus on one or both or each. But what makes you excited about like what's coming down the pike, and or maybe what keeps you up at night?
I mean, capacity is constantly increasing, and that is true from the long haul to the ultra short reach. It's across the board, and there are very different boundary conditions that need to be solved in submarine systems compared to intra-chip interconnects. So, and all of them are capacity and speed constrained and I/O constrained these days. And working in an I/O constrained area right now is just there are many more problems than you can even hope to find answers for. So that's just exciting by itself.
Thank you, Peter.
I still see many challenges in the modeling of these fibers, and that tunes me personally. And there are various propagation effects that are understood individually, but their interplay is a completely new game. So I think that is really interesting for also for students that want to find a path in this domain.
Okay, viewpoint from optical fiber and cable. I think that it is very interesting how we can manage modal status in the deployed cable situation. This is because we can design some type of few mode fiber or a coupled multiple fiber, but these modal property strongly relate with the deployed conditions. So I believe that we need further harmonization between fiber and cable design techniques.
Perfect. Thank you so much. And we're coming up right on 6 o'clock. So thank you to the panelists for the excellent presentations and for letting us pick their brain a little bit with our questions and answers. And thank you to everybody for participating in the webinar. And we will share a recorded version with those who couldn't join us today. And also, if you'd like a copy, you'd get it by email. So thank you again, everybody. And don't forget to check out the special issue. Thanks.
Thank you. Bye.
Thank you.
Thanks, bye.